Hello everyone. This presentation today is going to be about erosion in Australia, what it is, and to present the findings of some experiments conducted by the land rehabilitation students of UWA. Firstly, I, Lachlan Perry, will be speaking, followed by my friend Tarnee Rutherford. Erosion is the act in which earth is worn away, often by water, wind, or ice. A similar process, weathering, breaks down or dissolves rock, weakening it or turning it into tiny fragments. No rock is hard enough to resist the forces of weathering and erosion. Erosion, although being often a very slow, gradual breakdown and redistribution of sediments, can often be the most destructive, leaving a negative and long-lasting legacy on the land it scars. The process of erosion moves bits of rock or soil from one place to another. Most erosion is performed by water, wind, or ice in the form of glaciers. These forces carry the rocks and soil from the places where they were weathered. If the water is muddy, it is a sign that erosion is taking place. The brown color indicates that bits of rock and soil are suspended in the water and are being transported from one place to another. This transported material is called sediment. So, next up is water/fluvial erosion. Fluvial water or water erosion is another of the major agents of erosion. Rain carries away bits of soil and slowly washes away rock fragments. Rushing streams and rivers wear away at their banks, creating large and larger valleys. The best known example is the Colorado River creating the Grand Canyon. Another prime example is the weathering of the oceanic cliffs, creating caves. Wind is also another agent of erosion. It carries dust, sand, and volcanic ash from one place to another. Wind erosion can be very slow or very fast, slowly but constantly wearing away at rocks and transporting sediments across vast tracts of land. Ice is one of the more unknown agents of erosion. Ice can erode the land often more than any of the other agents. Glaciers move slowly downhill and across the land, picking up everything in their path, from tiny grains of sand to huge boulders. The rocks carried by a glacier rub against the ground below, eroding both the ground and the rocks. Glaciers grind up rocks and scrape away at the soil. Moving glaciers gouge out huge basins and form steep-sided mountain valleys. Several times throughout Earth's vast history there have been many ice ages and mini-ice ages, where huge glaciers have covered much of the northern hemisphere. The Finger Lakes in New York are the best-known example of glacier-induced erosion. It is worth noting that humans have evolved to have a very large impact on erosion. Farming practices such as deforestation have led to a huge increase in erosion in some areas of the globe. Tree roots hold down the soil and keep it compacted, and when these roots are uprooted, the soil becomes loose and prone to wind and rain erosion. However, humans have also greatly reduced erosion in some areas by building structures that physically prevent erosion from occurring. Severe erosion can lead to many detrimental effects in Australia, such as salinity and desertification. These are both very deadly to the health of ecosystems and have plagued Australia for generations. Desertification is a type of land degradation in which a relatively dry land region becomes increasingly arid, typically losing its bodies of water as well as vegetation and wildlife. It is caused by a variety of factors such as climate change and human activities. Salinity is a cause of dryland salinity is erosion that exposes saline subsoils. The removal and loss of native vegetation, as well as some agricultural practices, can increase erosion rates and expose naturally saline subsoils. The erosion cycle is a very important cycle occurring in nature. It has always been occurring and always will be occurring. The erosion cycle was first proposed by William Morris Davis in 1909. Davis defined the fluvial erosion cycle into three stages: a young, mature, and old sequence in the development of river valleys and the landscape the rivers were eroding. His basic concept includes a rapid tectonic uplift followed by a cessation of the land, which allows the rivers and streams to reduce the surface to a level close to sea level. During this uplift, Earth is subjected to erosion via wind and precipitation, and is subsequently eroded and redistributed. In his model, Davies determined the limitation of erosion on land and concluded that sea level is the ultimate base level for erosion, and that all erosion revolves around oceans and other bodies of water, preceded by an uplift in land. The cycle of erosion, as envisioned by Davis, has its initial stage at a time when the landmass is rapidly elevated by internal Earth forces, followed by a very long period of tectonic quiescence. Once raised above sea level as a landmass, streams come into existence and erosion begins to operate on the uplifted mass, which is gradually worn down almost to a plain. The landmass may, at some later time, be rejuvenated and the cycle begins again, and remnants of the earlier cycle of erosion are preserved at a new and higher levels. In a normal cycle, three stages have been recognized: as a youth stage, mature stage, and an old stage. These follow each other in a regular sequence. The youth stage. In this stage, the river flows along an uneven surface and there is intensive bottom erosion. The gradients are steep and the erosion is rapid. The rapid deepening of the channel leads to the formation of V-shaped valleys. Thus, during the youth stage of a river, the valley form undergoes vigorous development, particularly in the depth and the headward growth. Lakes, rapids, waterfalls, steep-sided valleys, and gorges are a common occurrence during this stage. The mature stage. In this stage, rivers attain a profile of equilibrium. The landmass is fully dissected/developed, and a well-integrated drainage system is developed. Ridges and valleys develop prominently. Floodplains develop and river meandering takes place. The topography consists of features such as mesas, meanders, lakes, natural bridges, floodplains, and alluvial fans. The old stage. In this stage, the slope is gentle and the velocity is low. The river loses most of its erosive power and flows in a sluggish manner. The river at this age does little erosion and transportation, but is mostly engaged in deposition. This stage is characterized by the development of distributaries, and the river flows almost at the base level of erosion. Most of the cycles of erosion do not reach their final stage, as sometime during their operation either climatic or tectonic disturbances take place, and thus results in an incomplete or partial cycle. The report. The students of land rehabilitation in 2015 at the University of Western Australia carried out several experiments discovering much about erosion on various topographic landscapes. 2 outdoor tests were conducted simulating monsoonal rainfall on both heavy and light rock-covered Pilbara soil. Heavy rock cover makes the velocity of runoff slower as it is inhibited by large rocks blocking the path. The transport capacity of the flow is also decreased. The flow will be unable to carry sediments as efficiently as they will be blocked and caught by rocks. There will also be many small pools where the rain falls into rock cavities. The larger downfall events, the rain will create and find preferred runoff paths through the heavy rocks, and this path will be eroded and scoured heavily while the rest remains relatively low in runoff. Light rock cover is expected to produce the opposite of heavy rock cover. The surface flow will be higher in velocity and will be able to transport sediments much more efficiently as they are uninhibited. Surface flow will be smooth and erosion will be relatively high. 3 tests were conducted indoors in large containers full of Pilbara soil placed on an incline. These containers full of Pilbara soil were constructed to mimic different topographic structures. These were flat terrain, a concave terrain, and a convex terrain. The flat surface terrain was constructed to mimic a terrain devoid of topographic structures such as hills or depressions. The flat terrain is expected to receive results of relatively high runoff and erosion as there is little to obstruct the flow or precipitation and eroded sediment. Concave slopes curve inwards, forming a sink or depression which collects erosion and runoff in a pool. The pool collects more infiltrated water over time. Any erosion that occurs will be collected in that pool and will sit there. The concave slope would have a high to low flow velocity as the flow would be normal until it encountered the pool or concave dip. Unless the precipitation was very intense and had a long duration, which led to the pool created in the concave depression to fill up, the erosion and runoff would be high to low. Convex terrain generally has a steady flow at the beginning of the slope. Once the runoff has created a detour over or around the convex mound, the runoff and erosion rates would intensify. However, this hypothesis is heavily dependent on the structure of the slope and the position of the obstructing convex mound. If the mound is towards the top, the initial flow and erosion would be slow and would speed up over time as the water found or created its preferred path. If the mound was far towards the bottom of the slope, the erosion and runoff would be slow for a much longer duration, as it would have to traverse the length of the slope before encountering the obstructing mound and then creating its preferred path. After this, however, the velocity and erosion would increase. Now we move on to the aims of the experiments conducted. The aims of the experiments conducted in the final weeks of land rehabilitation were to simulate runoff in a controlled indoor experiment and an outdoor rainfall experiment, and gather silt data and runoff rate data to determine to what extent topography impacts erosion. The hypotheses. It was hypothesized by the students that for the outdoor rainfall simulation experiment that the erosion would be initially slow for both heavy and light rock cover. The velocity and erosion would start to increase soon after the initial lull in runoff for the light rock cover, as the precipitation would reach the bottom of the container sooner than the heavy rock-covered containers. The runoff and erosion would take longer to reach the bottom of the container where it poured out into containers in the heavy rock cover experiments, as the rocks would form obstacles for the runoff. The indoor experiment. It was hypothesized that for the 3 experiments conducted indoors simulating flat, concave, and convex terrain, that the runoff and erosion would be initially slow and would intensify over time. For the flat terrain, the hypothesis was that it would take the least amount of time for the runoff to begin, as it would be unobstructed along the surface. The concave was hypothesized to take the longest, as there would be a depression somewhere along the surface which would act as a pool and deter the vast majority of runoff reaching the collection point until the pool was filled up. The convex train was hypothesized to achieve results in the middle of the first two. The convex structure was a mound or small hill that would act as an obstacle to runoff collecting sediment. The runoff would slowly create a preferred path before continuing its descent, gaining velocity. Methods. There were many methods employed for the experiments conducted by the students of land rehabilitation. The methods used for the outdoor rainfall experiment were extensive and controlled, collecting runoff rates and more importantly erosion via runoff. Firstly, the rainfall machine simulated monsoonal rainfall every 10 seconds for 40 minutes over light and heavy rock cover. 3 containers full of Pilbara sand were set up on a 30-degree incline below it. 15 containers were allocated to each container to sit at the bottom of the inclined container where a pipe sat channeling runoff. These containers were placed collecting runoff for 30 seconds every 2 minutes 30 for the duration of the experiment. There were 4 containers placed strategically around the containers, collecting rainfall that missed the containers. A large bucket which had a hose feeding into the rainfall simulator was controlled by 2 students who kept it full of water. After the experiment was concluded, the 15 containers full of silt and water from the 30 seconds of collecting were placed in an oven for 48 hours. Early in the following week, the containers were collected and weighed with the silt, and their weights were recorded. The next step was to clean out all the silt using dustpan brushes and then weighing them again and recording the difference, hence determining how much erosion had occurred through runoff. This was conducted for both heavy and light rock cover experiments. The indoor experiment employed many methods. Similar to the outdoor experiment, 3 large containers were placed on a 30-degree incline and filled with Pilbara soil measuring runoff rates. The experiment was carried out over 2 weeks. The first group carried out the experiment with a concave sand layout, and the second group carried it out with a convex mound along with a flat surface experiment. A large container was filled up with the sand, and a large convex mound was created at the halfway point of the container. This mound simulated runoff rates over a hilly terrain and would determine the impact terrain had on runoff rates. A rainfall simulator was rigged hanging above the container. The rainfall simulator was fed into the tap of a sink nearby, which was turned on at a determined pressure of 230, to ensure that all 3 experiments running had the same rainfall intensity. The experiment was designed to be run for an hour, however, due to lack of time and preparation, combined with the weighing of previous week's silt weights, the experiments only ran for 40 minutes. Throughout the experiment was hooked up to a runoff collector which measured runoff and fed the data into a computer program, which in turn collected the data and accumulated it in the form of an Excel sheet.
The results of the 2 experiments provided us with insights into erosion rates and runoff rates over different landforms within the Pilbara region. The differences between the concave and convex landscapes were clearly revealed, whilst overall revealing that erosion in the Pilbara is somewhat significant and can possibly be a big factor in shaping the landscapes of the future in that region. These next few graphs indicate the results of both the indoor and outdoor experiments. Unfortunately, in some of the results, not all of the catchment data was recorded, so there will only be 2 data series to go off. However, all still showed significant evidence that can then be backed up by scientific data. For the convex landscape erosion experiment, the results ultimately revealed that on a mounded surface, bounded by slopes of some kind, runoff as well as erosion rates increased significantly over time. From these 2 graphs provided, the increase in runoff rates is displayed, as well as the increase in sediment that has been eroded over time. They both increase over time due to processes that cause erosion. Raindrop splash onto the dry sandy soils will splash sand away from the center of the impact. Soils are significantly splashed downslope in this process, and with large amounts of rain from storm events, these soils can then be washed away or eroded. Thread flow, as well as the formation of rills, assist in the erosion of sediments as small channels are carved into the soil surface in which water accumulates and travels down, carrying sediment and silt with it. The lack of vegetation is an important factor in assessing why erosion is occurring on these soils. Vegetation on landscapes promotes greater infiltration. Most of the Pilbara soils can be barren, so the water is just infiltrating directly into the large, pored, sandy soil profile. However, this can build up over time and evidently cause flooding events. Within the concave landscape erosion experiment, it is evident that in landforms with a gape or dip in its landscape will exhibit reduced erosion rates and runoff rates over time. From the graph shown, The sediment weights collected over time roughly decreased despite the spike in Tray 2's weights. This indicates that the erosion rates had decreased over time. This is due to the process of sediment deposition. Initially, as rainfall comes in contact with the soilscape, sediments are splashed away and eroded. They can also be washed away in runoff. However, due to the concave landscape, these sediments, rather than continually eroding away, actually build up through deposition. An example of this is Lake Argyll in the Northern Territory, which within the next few centuries will continue to become smaller in size due to the constant deposition of sediments, making the catchment smaller and smaller each year. Runoff rates within the concave landscape start to build up to a point, but then they start to decrease. This is because the runoff starts to pond in the concave formation of the landscape. Evident from these two comparison graphs, convex landscapes show major signs of weathering and erosion when compared to concave landscapes. Convex landforms exhibit a spike in erosion rates, whilst concave landforms seem to fluctuate, slightly increasing and decreasing again over time. This is dependent on sediment deposition rates. Convex hill slopes have a much greater and rapid runoff rate over time compared to the concave landscape, in which slows down over time and rather than gushing off the downward slopes like convex slopes, will pond within the gape in the landscape. These results were obtained from the rainfall experiment conducted outside. Within the outdoor rainfall simulation experiment, erosion rates as well as runoff rates peaked within the first 3 to 12 minutes of precipitation, however then decrease over time. Runoff rates peak within the first few minutes of the experiment due to high-intensity rainfall thoroughly soaking through the soil profile and runoff starting to flood from it. The dramatic drop is a sign of the slope stabilizing itself through the process of self-armoring and the runoff becoming lower over time. There are peaks in runoff at 24 minutes as well as 30 minutes, and they are present because it indicates that the soil profile was fully saturated and could no longer retain any precipitation infiltration as it reached its threshold, and the water already in the profile was forced out very rapidly and in large quantities. Erosion rates peak during the first 3 to 12 minutes of the experiment in conjunction with the peak in runoff rates. This is because as the rainfall fell onto the dry sandy soils, lots of sediment debris became displaced through the raindrop impact and became washed off with the high rates of runoff. However, over time, the erosion rates continued to drop because as the soil profile became saturated, there were little sediments that could be loosened on the surface. Evident from the average runoff and erosion rates, there is a relationship between erosion and runoff in the first 3 to 12 minutes of the experiment, with erosion and runoff rates peaking. However, over time, erosion rates drop dramatically and become directly proportional to runoff rates. As runoff stays at fairly high amounts over time, erosion rates decrease. This is because the raindrop impact, thread flows and ponding that occurred at the start had already displaced and eroded away the vulnerable sediments. Erosion peaks within the first few minutes as the high-intensity rainfall washes all the dry and displaced sediments away from the soil profile. Gradually, as the profile is soaked by the monsoonal rainfall events, the erosion rates decrease to a very low and steady state. Runoff is generally directionally proportional to erosion rates, instead of in the first few minutes of the experiment. Over time, as runoff increases, erosion rates decrease on this Pilbara simulated catchment due to the initial sediments already being eroded away. In summary, it can be concluded that the convex landscapes exhibit greater erosion and runoff rates than the concave landscapes and hill slopes. This is due to processes revolving around erosion, including the raindrop effect, thread flow, formation of rills, and sediment deposition. Runoff rates, mainly through subsurface flows, are large in the Pilbara region due to the high porosity of the large pored sandy soils of the landscape, and erosion on the convex landscapes will shape landscapes in the future. Erosion impacts convex landscapes by weathering away the substrates, whereas in concave landscapes, erosion actually builds up the landscapes through deposition. It is noteworthy to take into account that studies have been done on the Pilbara and surrounding Gascoyne regions, which reveal that these areas have the highest amounts of soil loss due to erosion in the whole of Australia. The erosion rates will continue to remain fairly constant in the Pilbara region, and will continue to carve and create the beautiful landscape that we call the Pilbara. This concludes Lachlan Perry and I's short 20-minute video for the EART3339 unit on soil erosion processes and laboratory experiments conducted with the class. We thank you for the time to listen to this, and feel free to comment below. Thank you.